everyone, this is a technical explanation of the Rogowski Coil Integrator Senior Project for Team 18 from Grand Valley State University. Our sponsor is RoMan Manufacturing. The Rogowski Coil Integrator is for a Rogowski coil, which is a current transformer for alternating current. There's a large conductor put through the center of the Rogowski coil, which induces a magnetic field due to the amount of current. That magnetic field then it creates a voltage in the coil, which then that voltage is driven to our Rogowski coil integrator. The integrator will then turn that voltage back into a current that's proportional and readable from the original conductor.
The Rogowski Coil Integrator is capable of creating an output between 0 and 5 amps RMS AC current that is proportional but scaled down compared to the input current. The phase variation has to be below 0.5 degrees, and the current accuracy error has to be below 0.5% for ambient temperatures between 0 and 60 degrees Celsius. The user needs to be able to select input current values between 0 and 20,000 amps with 500 amp intervals through selector switches, and the power draw has to stay below 40 watts at full load.
Shown is the function overview of the Rogowski Coil Integrator. As you can see, there are 3 inputs and 1 output. The 3 inputs are a power supply of 24 volts, the Rogowski Coil output voltage as discussed earlier, and user switch input to affect and change the amplification of the Rogowski Coil voltage. And then we have a final output of 0 to 5 RMS current.
This is an overview of the full schematic of our circuit. So starting from the top left, we have the hot swap circuit, and then going right, we have the switches, and then we have the power supply and step-down converters and the primary switching amplifier, and then feeding that into the next circuit, we have the buffer amplifier, and then that feeds into the voltage to current converter, all of which we will discuss in more detail in the next slides.
The first circuit receiving the 24 voltage input is a hot swap and current control circuit. This circuit is built to act as reverse voltage protection and it has a charge pump that will control the amount of current being driven through the circuit to help protect components throughout and later aspects of the Rogowski Coil Integrator. The next circuit involved in the Rogowski Coil Integrator after the hot swap and current control is the DC to DC buck converter. This will turn the 24 voltage input verified by the hot swap and current control into a +9 output of a maximum of 3 amps. This is a complete module and chosen to help keep up with the project timeline and to make sure that it was efficient power is being delivered to the rest of the system. The hot swap and current control circuit also feeds into the DC-DC inverting converter, which will convert the 24 voltage input confirmed by the hot swap and current control into a -9 volt output at a maximum of 2.77 amps. This was also chosen to keep up with timeline and to make sure that the rest of the circuit is being provided with efficient and stable power for an efficient and stable Rogowski Coil Integrator as a whole.
Okay, so this is the primary amplifier that is being used for this circuit. We're using the OPA 2188 recommended by TI, and it was designed for this application. Pretty much our goal is to take the input signal and scale it to about 7.07 volts based on our input current. And this does scale linearly, so if you give it that expectation of the maximum of 7.07, but you give it a smaller signal, it will scale it linearly down to whatever value is needed. So in order to have variable values to go between 500 to 20,000 amps in those 500 amp intervals as requested, we used 4 switches, each of which has different resistor values on each position, and using a table we are able to select different positions to create a combination of resistors that give us our desired gain. And that is based off of taking that resistor value and using a non-inverting configuration, dividing it by an input resistor of 1300, add 1, and that gives us our total gain required for this. Okay, so the next circuit is the active integrator, and this is needed to correct for the negative 90-degree phase shift that is caused by the Rogowski coil. And this uses the second channel of the OPA 2188 from the primary amplifier. So what this does, in order to correct the 90-degree phase shift, it goes into another amplifier that uses some capacitors and resistors in parallel to change the rise time value so it can be corrected. So in this right image right here, we have two capacitors. One's for 50 hertz and the other is for 60 hertz. And they're both in parallel with this 100K resistor. And in order to swap between the two, it has a singular switch. And that switch allows you to select between 3.0 microfarads for the 60 hertz line and 3.6 microfarads for the 50 hertz line. Okay, after the active integrator, we feed the signal into a buffer circuit, and this is just a simple feedback circuit with a DC blocking capacitor just in case there's any additional offset from being amplified. And the point of this circuit is just to act as an infinite impedance between the previous amplifiers and the voltage to current converter, just to make sure there's no interference between the two sub-circuits.
This is the voltage to current converter. It is a push-pull circuit with two Darlington pair BJTs. One is in NPN and one is the PNP. The output current is measured across R5, which is the load resistor, and it's measured using an ammeter. This is the expected RMS output of the voltage to current converter. RMS stands for root mean squared, which means the first 20 milliseconds or so of this simulation can be neglected due to it not having enough data points. But as you can see, at max input signal, the expected RMS output is 5 amps. The top PCB is shown here with all this user interface switches. The bottom PCB is shown here, which includes all the other electrical components. It has the two input terminals for the Rogowski coil and the power supply. And it also includes the output terminal, which is used to measure the current using an ammeter. This is a very simple schematic of the thermal management plan for the project. The integrator needs to be in a full enclosure to avoid interference, so in the absence of convection, a conduction path was designed instead. The BJTs, seen in the picture, are two components in the voltage to current converter circuit, and each of them draws 26 watts of power. The thermal plan focuses on creating a path with very low thermal resistance so that the heat created can be dissipated effectively to protect all components from heat damage. As seen in the schematic, heat will move from the BJTs to a thermal pad, then to a piece of aluminum connected to the housing, which is also made of aluminum, and finally to the heatsink, which will dissipate the heat to the surrounding air. Using mostly aluminum makes the conduction path particularly effective in lowering the thermal resistance, which was calculated to be about 2 degrees Celsius per watt. Doing a worst-case scenario analysis in which the maximum power is 26 watts and the ambient temperature is 70 watts, the estimated maximum temperature of the BJT is 122 Celsius, which is below the maximum rating of 150 Celsius, which will help ensure longevity and good performance for the parts.
Hello everyone, this is our Rogowski Coil Integrator prototype, so if you want to come in and take a look, we have, to start off just for power, we're going to have a power supply here that's supplying 24 volts, and then that's going into two voltage converters, which is a negative voltage converter here and a positive voltage converter here. This is for negative 9 volts, and this is for a positive 9 volts.
Okay, so feeding from there into our first input circuit, we have this input terminal where our expected Rogowski coil integrator signal is going to go into, and that will feed into the primary amplifier and the active integrator. They're all in one package, and these two wires feed onto this board, which allows us to select those switches as mentioned in the slides. So that allows us to select the resistor value, and then this right here, this switch allows you to select between the 50 hertz and the 60 hertz capacitor as needed based on your input signal. And then those feed into this buffer circuit, which just provides infinite impedance, so it can feed safely into the voltage to current converter.
For the voltage to current converter, we have our IC here, and we have our two BJTs. This is the PNP and the NPN, and the current probe is attached here to the two terminals, and our load resistor is right there.
Okay, so we're gonna do a quick little demo just to show that this works. We're giving it an input signal of 250 millivolts right there. And if Brett could power it on, so we can just show you it working with some settings. Okay, so as you can see on this is our current probe.
Which has an offset due to special features of this probe, but the output that we see is the expected output, just at a different offset due to the actual current probe settings.